we have an attempted proof that x equals half is the only real root of this cubic, and here's the solution. I need to explain the error in the above attempt, and it is here to here. So essentially, if you have AB equal to a half, it does not imply A equals a half or B equals a half. This is the mistake. It does work if it's equal to 0. If AB is equal to 0, then either this is 0 or this is 0, or both, in theory. But not for other numbers. For example, A could be 2 and B could be a quarter. There's just lots of other possibilities. Whereas for 0, you have to have something as 0 if you're multiplying two numbers to get 0. We need to give a correct proof that then the x equals a half is the only real root of this cubic. Okay, let me go down here. So when x equals a half, we're going to get 1 over 8 plus 3 over 8 minus a half equals 4 over 8 minus a half, which is equal to 0. So x equals a half is a root. Important just to show that. Now, we've got x cubed plus 3/4 x minus a half equals 0. This implies if I times through by 4, get rid of the fractions, and x equals a half means 2x minus 1 is a factor. Using the factor theorem. So we can work out what we're left with. If we do polynomial division or another method of your choosing. Okay, we're going to get 2x squared then 2x into 2x squared will give x. Two x into 4x will give plus 2. Okay, write that as a single or two brackets together. Now we're not expecting to get any solutions from this, so let's consider it and show that there are no solutions. We can look at the discriminant, which is b squared, which is just 1 minus 4ac. And this is less than 0, so no real solutions. Therefore, x equals a half is the only real solution. Okay, good job so far. Right, back to here. we're now given a different equation. And we're told that alpha and beta are real. Alpha is not equal to 0. And we have a real root to x equals alpha. Find and simplify an expression for beta in terms of alpha. Prove that alpha is the only real root provided. There's quite a lot to recall there, so I'm just going to bring the whole question down. So x minus alpha is a factor. And we also know, okay, we can substitute alpha in. It must be that alpha cubed plus beta alpha minus alpha is equal to 0. We know that alpha is not equal to 0, so we can divide through. Alpha squared plus beta minus 1 is equal to 0. Therefore, beta is 1 minus alpha squared. Okay, that wasn't too bad. Now prove that alpha is the only real root, provided that this is true. Well, I'm going to go along a similar path now. Although first things first, I'm going to change it. So we've got we have x cubed plus 1 minus alpha squared x minus alpha equals 0. And I'm going to divide by the root, so x minus alpha. Okay, x is into x cubed, go x squared times, multiply through. It's a little bit weird, but you know, just do it exactly as you would with numbers. You just don't know what alpha is, because we're trying to prove it's true for all alpha, essentially, except, well, provided the modulus is less than 2. Okay, x is into alpha x squared, go alpha x. Now this is going to give me, I've got minus alpha x squared, and I'm minusing minus alpha x squared, so that's going to disappear. So we're just going to be left with x here, I think. And then finally, x is into x, go once, multiply through. Going to get 0. Okay, going to do the same again now. Consider the roots of this. Remember, let's just recall what we're trying to do. We found an expression for beta, so we substituted in for it. And now we're trying to prove that alpha is the only real root, provided that this is true. The discriminant is then going to be b squared minus 4ac. So this is negative, and alpha squared minus 4 is less than 0. I tend to try and factorize to solve these. Actually, this is a difference of two squares. And this is a quadratic inequality. So we've got one root at 2, one at minus 2, and one at 2. If I was to sketch this curve y equals this, plots y against alpha, then it would look as follows. And so the solutions are that it's minus 2 less than alpha, which is less than 2, or equivalently the modulus of alpha is less than 2. So I just need to write a conclusion. So alpha is the only real root. So no real roots for the modulus of alpha less than 2. Therefore, alpha is the only real root to, I think it was a capital I, or was it a 1 to I, provided okay. I think that's convincing. Finally, we look at the final part to this question. It's pretty epic. An examiner chooses a positive number alpha, so that alpha is the only real root of equation I. But the incorrect method used by the student produces 3 distinct real roots. Find the range of possible values for alpha. Okay, let's do this. Alright, first things first. It says an examiner chooses a positive number alpha so that alpha is the only real root of equation I. So it must be that the modulus of alpha is less than 2. But the incorrect method chosen by the student produces 3 distinct real roots. So we need to start off with this equation again. But in this time, we're going to be using the student's incorrect method. So they got the number onto the other side, and then they factorized out the x, and then they set them equal. Strange doing maths using an incorrect method to see what happens, but yeah, that's what we're doing. Just remembered actually, don't we also have that beta? I forgot this. We showed earlier that beta was 1 minus alpha squared, so I'll bring that in a second. So now we're interested in where we get 2 roots here. And we can write, therefore, x squared equals alpha squared plus alpha minus 1. Like I could go to the discriminant for this, but because there's no x term, I can simply look at this situation and I can say that this thing on the right must be positive to get another 2 roots. I'm actually gonna solve it equal to 0. This doesn't factorize. So it's minus 1 plus root 5 over 2, or minus 1 minus root 5 over 2. So to solve that inequality here, we've just worked out the roots. This one's going to be negative. Let me call this, I don't know, capital A, capital B. This one will be positive because root 5 is bigger than 1. It's a positive quadratic. Not entirely sure, sorry, where about the symmetry and so on, but that's what it's going to look like. So if we need it to be bigger than 0, then we actually need alpha is less than minus 1 minus root 5 over 2. Or alpha is bigger than minus 1 plus root 5 over 2. Now, we're not quite done because remember, this is true as well. Because that is for, that was so using the correct method, we only got one solution. Incorrect method gives us 3 solutions. That's what we need. Yeah, just recap what is going on here. So this purple one, these are the conditions so that the incorrect method gives 3 real roots. And in green, we needed this condition. Correct method only gives 1 real root, which was alpha. So now we need to put this together. And this thing here, this minus 1 plus root 5 over 2, that is going to be less than 2. So it's like I can put my 2 here, and I'm interested in this region. And then over here, I've got my minus 2, and I'm interested in this region. Hence, it's going to be minus 2 is less than alpha, but this is less than minus 1 minus root 5 over 2. Or we've got that b minus 1 plus root 5 over 2, and this is less in alpha, which is then less than 2. Those are the final solutions to this. Okay, well done if you got there. I thought, to be fair, I thought this question wasn't too bad. Here, and yeah, this last bit is, it's quite technical and easy to make mistakes in, I think, but that's it. This is the answer.